All right, folks, we're going to graph this rational function right here. And in order to graph this rational function, we have to be able to identify several important qualities about the graph of a rational function, which you've already been working on for the last few days. So here's what we're going to do. You have to remember how to identify all these qualities from this function. Then we're going to take all those qualities and we're going to graph them over here on a coordinate plane and draw the curve of the graph. Now, there's something very important you need to know. In most cases, in fact, in almost every case, there is at least one of these qualities, sometimes two or three of them, that do not, that a particular function, they just do not have them. It is possible for a function to not have a Y-intercept, to not have an X-intercept, not have a hole, and then maybe not have a vertical asymptote, and then it has a horizontal asymptote but not a slant asymptote. That can happen where it only has one of these qualities. Now you have to know what all these qualities are, but what we're going to do in this first one is we're going to do one where it's only missing one of these qualities. So it's going to have, this one has 5 of these qualities, and we're going to show them on this graph. So the first thing we want to do is we want to factor the numerator and the denominator. Now sometimes the numerator and the denominator are not factorable, in which case you either can't solve for the 0 because there isn't one, or you would need to use the quadratic formula or some other technique. Sometimes a graphing calculator is the only way that you can answer some of these questions. But I'm making these easy enough that you can factor them, and you can, well, most of them you can factor, and you can start to understand what these look like on a graph. First thing I want to notice is there's an 8 in all of these, so I'm going to factor out an 8, and then what's left over is x squared plus 2x minus 8. Over, now down here, look at all these terms, I can factor out a 4. So I'm going to divide out a 4, and what's left? X squared minus 6x, and then 32 divided by 4 is positive 8. There we go. And now this quadratic and this quadratic, they can be factored even more. So this is going to become 8 times two numbers that multiply to negative 8 but add up to positive 2 are positive 4 and negative 2. So I got an x plus 4 and an x minus 2. Over, I've got this 4 here. Two numbers that multiply to 8 but add up to negative 6 are negative 2 and negative 4. So I've got an x minus 4 and an x minus 2. All right, now that it's factored, we can identify the X-intercepts. We can identify the Y-intercepts, or Y-intercept if there's any holes. And we can see right away, right from the beginning, we can see that there is a hole, right? So we're going to go ahead and cross that out. We're going to cross this out. We're going to cross this out. And we know that there is a hole at x equals 2, right? Now in the last video, you learned how to identify what the y-coordinate is on that hole. So we're going to do that now too. We're going to go ahead and take the 2 and we're going to plug it into the rest of this. We're going to have 8 times 2 plus 4, that's 6. Over 4, 2 minus 4, well that's negative 2. 8 times 6 is 48. 4 times negative 2 is negative 8. And 48 divided by negative 8 is negative 6. And so the hole is at the coordinates 2 and negative 6. In fact, now what I'm going to do is I'm going to go ahead and draw that on the coordinate plane. And I've already shown you how to draw a hole, right? So we go to the point 2, negative 6. Okay, so from here, 1, 2, 1, 2, 3, 4, 5, 6. And I'm just going to put an open circle there, indicating that there is a hole in the graph. So the graph is going to pass through that point, only it's going to skip over that point because it's a hole. All right? Now, we can identify the Y-intercept. We actually could have identified the Y-intercept a long time ago because we don't need to factor it to identify the Y-intercept. We just plug 0 in for x. So if I put a 0 here, and a 0 here, and a 0 here, and a 0 here, that makes this 0, this 0, this 0, and this 0. So I have 0 plus 0 minus 64 over 0 minus 0 plus 32. And that just gives me negative 64 over 32. And that is equal to negative 2. So there is a y-intercept. The y-intercept of the function is at the point 0, negative 2. If I go to the graph, and I go to 0 and negative 2, that's right here. I'll put a dot there. That's the y-intercept. All right, now let's move on to the x-intercept. To identify the x-intercept, we need it in factored form, and we need to cross out any holes. You don't want to set the numerator equal to 0 with a hole in there, because what you're going to find is you would then find that there's an x-intercept at 2, 0. But there is not an x-intercept at 2, 0. At 2, there is a hole at 2 and negative 6. No x-intercept there. Okay, so be careful about that. Do your hole first. Do your hole first. Then, or identify your hole first. Then you can look for your x-intercepts. Okay, so there's no x-intercept at 2 and 0. However, we do have another factor in the numerator. We have an x plus 4. And if we set that equal to 0, and then subtract 4 from both sides, we get x equals negative 4. So if x is negative 4, and on the x-intercept, the y value is always 0, so we have an x-intercept at negative 4 and 0. So if we go to negative 4, 1, negative 2, negative 3, negative 4, and 0, we'll put a dot. And you see here, there's a point here, there's a point here, and there's a point here. Now, before we start drawing lines, we need to find out where the vertical and horizontal asymptotes are, if there are any. Remember, the vertical asymptote is where the denominator is equal to 0. So we're going to set the denominator, x minus 4, equal to 0, and solve. Add 4 to both sides, and we get x equals 4. So there's a vertical asymptote at x equals 4. Now, the way that you graph that is you use a vertical dashed line. Kind of like if you were doing an inequality, you're graphing a linear inequality. But the dashed line basically indicates that the graph is never touching it. Okay, it doesn't include that line. So we're going to go over to x equals positive 4, 1, 2, 3, 4. And as a vertical line here, we are going to draw a dashed line. That vertical dashed line is representing the vertical asymptote. Now, none of the points on that vertical line, none of those points are a part of the graph. The reason we put that vertical line there is to indicate that the graph that we are drawing is getting closer and closer and closer and closer and closer and closer without actually touching, not touching you, I'm not touching you, without actually touching the line x equals 4, okay? So we draw a vertical line, dashed line at x equals 4. So now, last thing, remember, graphs don't have both horizontal and slant asymptotes. They can only have one or the other, right? So we have to decide, does this graph have a horizontal asymptote or a slant asymptote? Well, look at the powers. We have second power on the top, second power on the bottom. In order to be a slant asymptote, the power on the top would have to be 1 higher, right? Well, in this case, they're the same power. Well, remember the rule of horizontal asymptotes. If the powers are the same in the top and the bottom, then we simply do the ratio of the lead coefficients. So it's 8 over 4, right? Okay, so the horizontal asymptote is going to be at 8 over 4. And 8 over 4, what's 8 over 4 equal to? It's equal to positive 2. So there's a horizontal asymptote at y equals 2, right? So now we're going to go over to y equals 2, 1, 2, that's right here, and we're going to draw another dashed line, but this time it's a horizontal dashed line. So now we've got our vertical asymptote, we've got our horizontal asymptote, we've got our hole, we've got our y-intercept, there's only one x-intercept, there's no slant asymptote, so we're ready to draw. Now, here's the thing. What we've created here, you can see that we have 2 lines. Okay, for every section, there's always a section above the horizontal asymptote and below the horizontal asymptote. But the sections can be split up by vertical asymptotes. So there's another above and there's another below. Your graph cannot be both above and below the horizontal asymptote. In each section, it can only either be above or it's below. This one, we know, is below the horizontal asymptote because look at all these points that are on the graph. And so here's what we're going to do. We're going to draw a curve through these points. And here's what they have to do. The curve has to get, at the very ends, it has to get close to the asymptote. So that's kind of close. And then it's going to come over here, and it's going to go through this point. Then it's going to go through this point. Now it's going to look sort of weird there. It's not going to look perfect. It's a sketch. It's not going to be perfect. And then it has to go through this hole, right? But when it goes through the hole, we're not going to have it go. We're going to draw on one side of the hole and the other side of the hole. Then it has to get close to the asymptote. And that's about the best I'm going to do. That's part of this graph. That is part of the graph of this rational function. Now, when we go over to this side of the vertical asymptote, we have to decide whether it's going to be above or below. Now, I happen to know that it's going to be above, and I'll tell you why. I know it's going to be above because I know there's no X-intercept over here. And in order for it to be here, it would have to, at some point or another, cross over the x-axis. And I know that it's not going to cross over the x-axis because we only have one X-intercept, right? So I know that it's above. Now, just to make sure, I'm going to do what's called a test. I'm going to do what's called a test point. Okay, a test point. Now, a test point is where you just take a number in the area where you're trying to figure out, plug it into the original function, or I could even plug it into the factored function, and then find out what the output is. So I need a number that is on this side of the vertical asymptote, so on the right side of x equals 4. So how about x equals 5? Okay, so we'll take x equals 5. We'll put it in here. What's 5 plus 4? So here's what we're going to have. We're going to have 8 times 5 plus 4. 5 plus 4 is 9. And then 4 times 5 minus 4. 5 minus 4. So 5 plus 4 is 9. 9 times 8 is 72. 5 minus 4 is 1. 1 times 4 is 4. And 72 divided by 4 is 18. Okay? So we know that at x equals 5, the output value is 18, which is way up there. It's not even on the graph. But we know, here's what we know, is we know that the graph is going to pass through this section here. We don't know precisely where up here it's going to be, but we know that it's going to be over here. So here's what I'm going to do. Because I'm sketching it, it's not a perfect graph. I'm just going to roughly draw a curve that does this. And that's good enough. Okay? I don't really have any other. I could calculate the points and put them in there, but it's possible it wouldn't even show up on the graph. But that's it. Now, here's what I've done. Now, this is actually normal. This is kind of like what rational functions look like. Just to give you an example of what rational functions can look like a lot. They can have, let's say they have a vertical asymptote and a horizontal asymptote, and then they might do something like this. That's oftentimes what they look like. The graph of 1 over x, looks like this. It actually has the y-axis is its vertical asymptote, and the x-axis is its horizontal asymptote, and it does this. There we go. Because it doesn't cross over the vertical asymptote, and it usually doesn't cross over the horizontal asymptote. Sometimes it can, but it usually doesn't. Okay? All right. Well, I think that's it for now. For this video, what we're going to do is I'm going to come back in the next video. We're going to do another example with different kinds of qualities.